What if everything you thought you knew about the universe was just the tip of the iceberg? Imagine a reality where black holes could be gateways to other dimensions, or where time itself might flow backward in certain corners of the cosmos. These aren't just wild ideas from science fiction, they're real theories proposed by some of the brightest minds in science, and they challenge everything we think we understand about space, time, and existence itself. In this video, we're diving into 50 bizarre space theories that will make you question the very fabric of reality. From the possibility that our universe is a simulation to the mind-bending idea that multiple universes could be colliding right now, these theories push the boundaries of science and imagination. So buckle up and get ready to explore the strange, the mysterious, and the downright unbelievable. By the end of this journey, you might just find yourself seeing the cosmos in a whole new light. Let's begin. Now turning to our first theory, let's dive into the simulation hypothesis. This mind-bending idea suggests that our entire universe might not be real, at least not in the way we think. Instead, it could be an incredibly advanced computer simulation created by a civilization far more advanced than our own. The origins of this theory trace back to philosopher Nick Bostrom, who proposed that one of three possibilities must be true. Either advanced civilizations tend to go extinct before developing the ability to simulate reality. They choose not to create such simulations, or we are almost certainly living in one. Tech billionaire Elon Musk is one of the most vocal proponents of this idea, famously stating that the odds of us living in base reality are 1 in billions. But what does this mean for us? If true, it raises profound philosophical questions about the nature of existence, free will, and the purpose of life. Are we merely characters in someone else's game, or is there more to our simulated reality than meets the eye? This theory doesn't just challenge our understanding of the universe, it forces us to question the very nature of our existence. Now turning to our second theory, let's explore the holographic universe. This fascinating idea suggests that our three-dimensional reality might actually be a projection from a two-dimensional surface, much like a hologram. The roots of this theory lie in the study of black holes and quantum physics. Scientists discovered that the information about everything that falls into a black hole is somehow encoded on its surface or event horizon. This led to the idea that the universe itself could operate in a similar way, with all the information about our three-dimensional world being stored on a two-dimensional boundary. The implications are staggering. If true, it means that everything we see, touch, and experience could be a kind of cosmic illusion, a projection from a deeper, simpler reality. This theory also challenges our understanding of space and time, suggesting that they might not be fundamental but emergent properties of a more basic framework. Imagine looking at a movie screen and realizing that the entire film is being projected from a flat surface. It's a similar concept, but on a universal scale. The holographic universe theory doesn't just reshape how we see the cosmos, it forces us to rethink the very fabric of reality itself. What if the universe is far simpler and more interconnected than we ever imagined? This theory opens the door to a whole new way of understanding existence. Now turning to our third theory, let's dive into the multiverse theory, a concept that suggests our universe might be just one of countless others existing parallel to our own. Imagine a vast cosmic tapestry where each thread represents a separate universe, each with its own unique set of physical laws and constants. This idea isn't just science fiction, it's grounded in serious scientific exploration. One version of the multiverse theory, known as bubble universes, proposes that our universe is like a bubble floating in a sea of other bubbles, each one a separate universe with its own distinct properties. These bubbles could have formed during the rapid expansion of space in the early moments of the Big Bang, creating pockets of reality that are forever out of reach from one another. Another fascinating variation is the idea of quantum branching, where every possible outcome of a quantum event spawns a new universe. For example, if you flip a coin, in one universe it lands heads and in another it lands tails. This means there could be infinite versions of you, each living out a different life based on every possible decision ever made. The multiverse theory also offers a potential explanation for some of the strange anomalies in our universe, like the fine-tuning of physical constants that seem perfectly calibrated for life. If there are infinite universes, it's statistically inevitable that at least one would have the right conditions for life to exist. This theory doesn't just expand our understanding of the cosmos, it challenges us to rethink our place within it. What if every choice you make creates a new reality? What if somewhere out there, another version of you is living a completely different life? The multiverse theory invites us to consider the infinite possibilities that lie beyond the boundaries of our own universe. Now turning to our fourth theory, let's explore the Boltzmann Brain Paradox, one of the most mind-bending ideas in modern cosmology. Imagine this, floating in the vast emptiness of space, a fully formed, self-aware brain suddenly comes into existence, complete with memories, thoughts, and a sense of identity. This isn't the plot of a sci-fi movie, it's a serious theoretical possibility rooted in the laws of physics, specifically the concept of entropy. Entropy, a measure of disorder in the universe, tends to increase over time, but it also allows for random fluctuations. In an infinite universe, given enough time, even the most improbable events can occur. The Boltzmann Brain Paradox suggests that, statistically, it's more likely for a single, isolated brain to spontaneously form out of chaos than for an entire universe like ours to exist. This bizarre idea challenges our understanding of consciousness and existence. If such a brain were to form, it would have no connection to the physical world, yet it would perceive itself as real, complete with fabricated memories and experiences. This raises profound questions. How do we know our own consciousness isn't just a random fluctuation? Could everything we perceive as reality be an illusion created by a Boltzmann brain? The paradox also ties into the nature of the universe itself. If the cosmos is eternal and infinite, as some theories suggest, then the probability of Boltzmann brains forming becomes a significant concern for cosmologists. It forces us to confront the limits of our knowledge and the possibility that our understanding of reality might be fundamentally flawed. The Boltzmann Brain Paradox doesn't just stretch our imagination, it challenges us to rethink what it means to exist and whether we can ever truly trust our perceptions of the universe. What if everything we know is just a fleeting moment in an endless sea of chaos? This theory invites us to question the very fabric of reality itself. Now turning to our fifth theory, let's dive into the Big Bounce theory, a fascinating idea that suggests the universe doesn't have a single beginning or end, but instead goes through endless cycles of expansion and contraction. Unlike the traditional Big Bang theory, which proposes that the universe started from a singular, infinitely dense point, the Big Bounce theory imagines a cosmos that has been expanding and collapsing in a rhythmic dance for eternity. Picture this, instead of a one-time explosive event, the universe breathes in and out like a cosmic heartbeat. This cyclical model challenges the notion of a definitive starting point, offering an alternative to the Big Bang's linear narrative. But how could such a theory hold up? One key piece of evidence comes from the study of quantum gravity, which suggests that at extremely high densities, the laws of physics as we know them might break down, allowing for a bounce instead of a singularity. This means that when the universe contracts to its smallest possible size, quantum effects could prevent it from collapsing entirely, instead causing it to rebound and expand once more. The Big Bounce theory also aligns with certain observations in cosmology, such as the uniformity of the cosmic microwave background radiation, which could be explained by the smoothing effects of countless cycles of expansion and contraction. However, this theory isn't without its challenges. For one, it requires a mechanism to explain how the universe transitions from contraction to expansion without violating the laws of physics. Additionally, it raises questions about what existed before the first bounce and whether time itself is cyclical. Despite these uncertainties, the Big Bounce theory offers a compelling alternative to the Big Bang, inviting us to rethink the origins and ultimate fate of the universe. Could our cosmos be part of an infinite series of cycles, each one giving rise to new galaxies, stars, and life? This theory not only challenges our understanding of the universe's beginnings, but also opens up profound questions about its future. What if the Big Bang wasn't the start of everything but just one chapter in an endless cosmic story? The Big Bounce theory pushes us to consider the possibility that the universe is far more dynamic and cyclical than we ever imagined. Now turning to our sixth theory, let's explore the intriguing concept of white holes, often described as the cosmic opposite of black holes. While black holes are known for their immense gravitational pull, trapping everything, even light, white holes are theorized to do the exact opposite. Imagine a region of space-time where matter and energy are violently expelled rather than absorbed. Unlike black holes, which pull everything in, white holes push everything out, creating a kind of cosmic fountain. But here's the catch: white holes are purely theoretical. No one has ever observed one, and their existence remains a fascinating puzzle in the realm of astrophysics. So, where does this idea come from? The concept of white holes emerges from the equations of general relativity, the same framework that predicts black holes. In fact, mathematically, a white hole is like a black hole running in reverse. If a black hole is a one-way street into oblivion, a white hole is a one-way street out of it. Some scientists speculate that white holes could be connected to black holes through wormholes, forming a bridge between 2 points in space-time. This idea suggests that what goes into a black hole might eventually come out of a white hole somewhere else in the universe. But how could white holes fit into our understanding of the cosmos? One possibility is that they could explain certain high-energy cosmic events, like gamma-ray bursts, which release enormous amounts of energy in a short time. If a white hole were to suddenly expel matter and energy, it could produce a similar phenomenon. Another intriguing idea is that white holes might be the remnants of black holes from a previous universe, left over from a Big Bounce cycle. This would mean that white holes could be a window into the past, offering clues about the universe's history before the Big Bang. However, the biggest challenge with white holes is their theoretical nature. For one, they violate the second law of thermodynamics, which states that entropy or disorder always increases over time. A white hole, by spewing out matter and energy, would seem to decrease entropy, which raises questions about their feasibility. Additionally, the extreme conditions required for a white hole to exist make them unlikely to form naturally in our universe. Despite these challenges, the idea of white holes continues to captivate scientists and enthusiasts alike, pushing the boundaries of our understanding of space-time. Could white holes be real, or are they just a mathematical curiosity? Either way, they challenge us to think beyond the limits of what we know, inviting us to imagine a universe where the rules of physics might be more flexible than we ever imagined. What if white holes are out there, hidden in the depths of space, waiting to be discovered? This theory not only expands our understanding of black holes, but also opens up new possibilities for the mysteries of the cosmos. Now turning to our seventh theory, let's dive into the enigmatic concept of phantom energy, a hypothetical form of dark energy that could spell the end of the universe as we know it. Dark energy, the mysterious force driving the accelerated expansion of the universe, is already one of the greatest puzzles in cosmology, but phantom energy takes this mystery to an even more extreme level. Unlike ordinary dark energy, which causes the universe to expand at an increasing rate, phantom energy has a peculiar property: its density increases over time. This means that as the universe expands, phantom energy grows stronger, accelerating the expansion even faster. over billions of years, this runaway effect could lead to a catastrophic event known as the Big Rip. Imagine a scenario where the expansion of the universe becomes so rapid that it overcomes all forces holding matter together. Galaxies, stars, planets, and even atoms would be torn apart. The universe would end not with a bang, but with a violent, unstoppable expansion that rips everything to shreds. But how does phantom energy differ from regular dark energy? The key lies in its equation of state, a measure of how its pressure relates to its density. For phantom energy, this value is less than -1, meaning it exerts a repulsive force stronger than anything we've ever observed. This bizarre property is what makes phantom energy so destructive. If it exists, it could dominate the universe's future, leading to the Big Rip in as little as 22 billion years. The implications of this theory are staggering. Not only would it redefine our understanding of dark energy, but it would also force us to confront the ultimate fate of the cosmos. Could the universe really end in such a violent and dramatic way? And if so, what does that mean for the possibility of life or the existence of other universes? While phantom energy remains speculative, it challenges us to think about the limits of our knowledge and the fragility of the universe. It also raises profound questions about the nature of dark energy itself. Is it a constant force, or could it evolve into something more destructive over time? As we continue to explore the mysteries of the cosmos, theories like phantom energy remind us that the universe is full of surprises, and its ultimate fate may be stranger than we can imagine. What if the Big Rip is not just a theoretical possibility, but an inevitable reality? This theory pushes the boundaries of cosmology, inviting us to ponder the profound and unsettling possibilities of the universe's end. Now turning to our 8th theory, let's explore one of the most perplexing questions in science, the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" This paradox highlights the contradiction between the high probability of extraterrestrial life existing in the universe and the complete lack of evidence for it. Given the sheer size of the cosmos, with billions of galaxies, each containing billions of stars and planets, it seems almost certain that life should exist elsewhere. Yet, despite decades of searching, we've found no signs of intelligent civilizations. So, why haven't we encountered aliens? One possible explanation is the Great Filter, a concept suggesting that there's some kind of barrier that prevents life from advancing to the point of interstellar communication or travel. This filter could exist in our past, meaning that the emergence of intelligent life is incredibly rare, or it could lie ahead of us, implying that advanced civilizations inevitably destroy themselves before they can make contact. Another intriguing idea is the zoo hypothesis, which proposes that extraterrestrial civilizations are aware of us but choose not to reveal themselves, treating Earth like a protected wildlife reserve. They might be observing us from a distance, waiting for humanity to reach a certain level of maturity before making contact. Other theories suggest that advanced civilizations might be using technologies we can't detect, or that they've already come and gone, leaving no trace. The Fermi Paradox forces us to confront the possibility that we might be alone in the universe, or that the challenges of interstellar communication are far greater than we imagine. It also raises profound questions about our place in the cosmos. Are we unique, or are we simply too primitive to join the galactic community? As we continue to search for answers, the Fermi Paradox reminds us that the universe is full of mysteries, and the truth might be stranger than we can imagine. Could the silence of the cosmos be a warning, or is it simply a reflection of how vast and unknowable the universe truly is? This theory challenges us to rethink our assumptions about life, intelligence, and the future of humanity in the stars. Now turning to our 9th theory, let's dive into one of the most puzzling mysteries in modern cosmology, the dark flow theory. This theory revolves around the strange observation that entire galaxy clusters are moving in a specific direction at incredible speeds, as if being pulled by something far beyond the edges of the observable universe. This motion, detected through the study of cosmic microwave background radiation, defies our current understanding of how the universe should behave. According to the Big Bang Theory, the universe is expanding uniformly in all directions, with no preferred direction of motion. Yet, the dark flow suggests that there's something out there, something massive and unseen, exerting a gravitational influence on these galaxy clusters. Scientists have proposed that this mysterious force could be caused by structures or regions of space that lie outside our observable universe, perhaps remnants of the early universe or even other universes in a multiverse. The implications of this theory are staggering. If confirmed, it could mean that our universe is just one small part of a much larger, interconnected cosmic web, with other universes or dimensions influencing our own. It also challenges the idea that the observable universe is all there is, opening up the possibility that there's far more to reality than we can currently detect. The dark flow phenomenon raises profound questions about the nature of the cosmos and our place within it. Are we being pulled toward something unimaginably vast? Could this be evidence of a multiverse, or even a sign of a universe that existed before the Big Bang? As we continue to study this mysterious motion, the dark flow reminds us that the universe is full of surprises and that our understanding of reality is still in its infancy. What lies beyond the edges of our observable universe? Could this be the first clue to uncovering the true scale and complexity of existence? This theory challenges us to rethink the boundaries of the cosmos and consider the possibility that the universe is far stranger and more interconnected than we ever imagined. Now turning to our 10th theory, let's explore one of the most mind-bending ideas in modern physics, the quantum immortality theory. This theory suggests that consciousness might never experience death because it could continuously shift to alternate realities where survival is possible. At its core, this idea stems from the many worlds interpretation of quantum mechanics, which proposes that every possible outcome of a quantum event actually occurs, each in its own separate universe. For example, if you were in a life-threatening situation, the theory suggests that your consciousness would always find itself in a reality where you survived, no matter how unlikely that outcome might seem. This raises profound questions about the nature of existence and the limits of human perception. If true, it would mean that from your perspective, you could never truly die, only experience a series of realities where you continue to live. But this theory also brings up ethical dilemmas. If consciousness can escape death by jumping to alternate realities, what does that mean for our understanding of mortality? Does it diminish the value of life, or does it suggest that existence is far more complex than we can comprehend? The quantum immortality theory challenges us to rethink not only the nature of reality, but also our place within it. Are we truly bound by the laws of physics as we know them, or is there a deeper, more mysterious layer to existence that we have yet to uncover? As we ponder these questions, one thing is clear: the universe is far stranger than we ever imagined, and theories like this remind us that the boundaries of science and philosophy are constantly being pushed. What does it mean to be alive in a multiverse where death might not be the end? Could this be the key to understanding the true nature of consciousness itself? This theory invites us to consider the possibility that reality is not just what we see, but an infinite tapestry of possibilities waiting to be explored. Now turning to our 11th theory, we delve into one of the most perplexing mysteries in modern physics, the black hole information paradox. This theory centers on a fundamental conflict between two pillars of science, quantum mechanics and general relativity, and asks a seemingly simple yet deeply troubling question: is information lost forever when it falls into a black hole? According to general relativity, once something crosses a black hole's event horizon, it's gone for good, crushed into the singularity at the center. But quantum mechanics tells us that information can never be truly destroyed. It must be preserved in some form. This contradiction has puzzled scientists for decades, and it was Stephen Hawking who first brought it to light. Hawking proposed that black holes emit radiation, now known as Hawking radiation, which causes them to slowly evaporate over time. But here's the catch. If a black hole evaporates completely, what happens to all the information about the matter it once consumed? Does it vanish, violating the laws of quantum mechanics, or is it somehow encoded in the radiation? This dilemma has led to a flurry of theories and potential resolutions. One idea is the holographic principle, which suggests that all the information about what falls into a black hole is stored on its surface like a cosmic hologram. Another proposal is the idea of black hole firewalls, where the event horizon might be a region of intense energy that destroys anything crossing it, preserving information in the process. Yet another theory involves quantum entanglement, where information might be transferred to particles outside the black hole through mysterious quantum connections. Despite decades of research, the paradox remains unresolved, and it continues to challenge our understanding of the universe. What does this mean for the future of physics? Could resolving this paradox lead to a unified theory of quantum gravity, bridging the gap between the quantum world and the cosmos? The black hole information paradox reminds us that even the most well-established laws of science can be called into question, and that the universe still holds secrets we have yet to uncover. As we grapple with these questions, one thing is certain: the journey to understanding black holes and the nature of reality itself is far from over. What other mysteries might these cosmic enigmas reveal as we continue to explore the depths of space and time? Now turning to our 12th theory, we step into the fascinating world of time crystals, a concept so bizarre that it seems to defy the very laws of physics as we know them. Unlike ordinary crystals, which have repeating patterns in space, time crystals are structures that repeat in time. Imagine a clock that ticks not because of any external force, but because its internal structure is designed to oscillate endlessly, even in its lowest energy state. This strange behavior was first proposed by Nobel laureate Frank Wilczek in 2012, and it challenges one of the most fundamental principles of physics, the idea that systems in equilibrium should remain static. Time crystals, however, break this rule by exhibiting perpetual motion without any energy input, a phenomenon that seems to bend the laws of thermodynamics. But how is this possible? The key lies in the concept of symmetry breaking. Just as a traditional crystal breaks spatial symmetry by forming a repeating lattice, a time crystal breaks time symmetry by oscillating in a predictable, repeating pattern. This discovery has opened up a whole new realm of possibilities in quantum physics. For instance, time crystals could revolutionize quantum computing by providing stable, error-resistant systems for storing and processing information. They might also help us better understand the nature of time itself, offering clues about how time emerges from the quantum realm. But perhaps the most mind-bending aspect of time crystals is what they reveal about the universe. If structures can exist that repeat in time rather than space, what does that say about the fabric of reality? Could time itself be a kind of crystal with hidden patterns and rhythms we have yet to uncover? As we continue to explore this strange and uncharted territory, one thing is clear: time crystals are not just a scientific curiosity, they are a window into a deeper understanding of the universe. What other secrets might they hold as we push the boundaries of physics and venture further into the unknown? Now turning to our 13th theory, we delve into the mysteries of the cosmic microwave background, or CMB, and the strange anomalies that have left scientists questioning the very origins of our universe. The CMB is often described as the afterglow of the Big Bang, a faint radiation that fills the cosmos and provides a snapshot of the universe when it was just 380,000 years old. But within this ancient light, there are peculiar patterns that don't quite fit our current understanding of the Big Bang. For instance, certain regions of the CMB appear colder or hotter than they should be, and there are large-scale structures that seem to defy the principles of uniformity and isotropy, the idea that the universe should look the same in all directions. These anomalies have led some researchers to propose that the Big Bang might not have been the true beginning of everything. Instead, they suggest that our universe could be the result of a pre-existing state, perhaps a collision between two universes or the remnants of a previous cosmic cycle. This idea challenges the traditional Big Bang narrative and opens the door to theories like the Big Bounce or the multiverse, where our universe is just one of many in an endless cycle of creation and destruction. But what do these anomalies really mean for our understanding of the cosmos? If the CMB holds clues to a pre-Big Bang universe, it could fundamentally reshape our understanding of time, space, and the very nature of existence. Are we looking at the fingerprints of a universe that existed before ours? Could these patterns hint at a deeper, more complex reality that lies beyond our current models? As we continue to study the CMB and its strange features, one thing is certain. The anomalies in this ancient light are not just random quirks, they are profound puzzles that could unlock the secrets of the universe's origins. What other revelations might they hold as we peer deeper into the cosmic past? Now turning to our 14th theory, we explore the intriguing possibility of a hidden giant lurking in the outer reaches of our solar system planet 9. This hypothetical planet, thought to be up to 10 times the mass of Earth, has yet to be directly observed, but its presence is inferred from the peculiar orbits of distant objects in the Kuiper belt. These icy bodies, far beyond Neptune, exhibit strange clustering patterns that suggest the gravitational influence of a massive, unseen object. Scientists have calculated that the orbits of these objects are tilted and aligned in a way that can't be easily explained by the known planets alone. Enter Planet 9, a potential explanation for these anomalies. If it exists, this distant world could be orbiting the Sun at a staggering distance, taking anywhere from 10,000 to 20,000 years to complete a single trip around our star. But how could such a massive planet remain hidden for so long? The answer lies in its extreme distance and the faintness of its reflected sunlight, making it incredibly difficult to detect with current telescopes. The discovery of Planet 9 would not only solve the mystery of these strange orbits, but also revolutionize our understanding of how planets form and migrate. It could suggest that our solar system once had more planets, some of which were ejected into interstellar space or captured by other stars. This theory also raises questions about the early history of our solar system. Was Planet 9 always there, or was it captured from another star system? As astronomers continue their search, the hunt for Planet 9 remains one of the most exciting quests in modern astronomy. What secrets might this elusive world hold, and how could its discovery reshape our cosmic story? The answers could be out there, waiting to be found in the icy darkness of the outer solar system. Now turning to our 15th theory, we delve into the mysterious possibility that entire galaxies could be made entirely of dark matter, invisible to our eyes and instruments. Dark matter, which makes up about 85% of the universe's mass, doesn't emit, absorb, or reflect light, making it impossible to observe directly. Yet, its presence is felt through its gravitational effects on visible matter, like stars and galaxies. Scientists have long noticed that galaxies rotate faster than they should based on the visible matter they contain. This discrepancy suggests the existence of an unseen force, dark matter, holding these galaxies together. But what if some galaxies are composed almost entirely of this elusive substance? Enter the concept of dark matter galaxies. These hypothetical structures would be invisible to telescopes, detectable only through their gravitational influence on nearby objects. For instance, if a dark matter galaxy passed near a visible galaxy, its gravity could distort the light from the visible galaxy, a phenomenon known as gravitational lensing. This effect has already been observed in some regions of space, hinting at the presence of massive, unseen structures. The idea of dark matter galaxies could also explain why some regions of the universe appear to have more gravitational pull than the visible matter there suggests. If these galaxies exist, they might be scattered throughout the cosmos, hidden in plain sight. But how do we search for something we can't see? Astronomers are using advanced techniques, such as mapping the distribution of gravitational lensing effects and studying the motion of stars and gas in galaxies to uncover these invisible giants. The discovery of a dark matter galaxy would be a monumental breakthrough, shedding light on the nature of dark matter itself and its role in shaping the universe. Could these ghostly galaxies hold the key to understanding the universe's missing mass? As we continue to probe the cosmos, the search for dark matter galaxies remains one of the most fascinating and challenging quests in modern astrophysics. What other secrets might these invisible structures reveal about the hidden fabric of the universe? The answers could be out there, waiting to be uncovered in the vast, dark expanse of space. Now turning to our 16th theory, we explore the fascinating possibility of using quantum entanglement for instant communication across vast distances. Quantum entanglement is a phenomenon where two particles become linked, sharing a connection that persists no matter how far apart they are. When one particle's state changes, the other instantly reflects that change, even if they are light years apart. This strange behavior has led scientists to wonder if it could be harnessed for faster-than-light communication, a concept that could revolutionize interstellar communication. Imagine being able to send messages across the galaxy without the delays imposed by the speed of light. It sounds like science fiction, but quantum entanglement makes it a tantalizing possibility. However, there are significant challenges to overcome. For one, while entangled particles can share information instantly, we can't directly control or manipulate the information they carry. This means we can't simply encode a message into one particle and expect it to appear in the other. Additionally, the process of measuring entangled particles destroys their entanglement, making it difficult to use them for practical communication. Despite these hurdles, researchers are exploring creative ways to exploit quantum entanglement for communication. One idea involves using entangled particles as a kind of cosmic telegraph, where changes in one particle could signal information to its partner. Another approach focuses on quantum networks, where entangled particles could form the backbone of a future interstellar internet. The implications of such a breakthrough are staggering. It could enable real-time communication with distant spacecraft, colonies on other planets, or even extraterrestrial civilizations. But beyond the practical applications, quantum entanglement communication challenges our understanding of physics itself. It raises questions about the nature of reality, the limits of information transfer, and the fundamental rules that govern the universe. Could quantum entanglement be the key to unlocking the cosmos's communication potential? As we continue to unravel the mysteries of quantum mechanics, the dream of instant interstellar communication remains one of the most exciting frontiers in science. What other secrets might quantum entanglement hold, and how could they reshape our place in the universe? The answers may lie in the strange, interconnected world of quantum physics, waiting to be discovered. Now turning to our 17th theory, we delve into the enigmatic mystery of Tabby's star and the intriguing hypothesis that its unusual dimming could be the result of an alien megastructure. Tabby's star, officially known as KIC 8462852, has baffled astronomers since its discovery. Unlike most stars, which dim and brighten in predictable patterns, Tabby's star exhibits irregular and dramatic dips in brightness, sometimes by as much as 22%. These fluctuations are so unusual that scientists have struggled to explain them using conventional astrophysical phenomena, such as planets or dust clouds. This has led to the bold speculation that the star's dimming might be caused by a massive artificial structure, possibly built by an advanced extraterrestrial civilization. The idea is that such a structure, often referred to as a Dyson sphere or swarm, could be harvesting energy from the star, causing the observed dimming. A Dyson sphere is a hypothetical megastructure that surrounds a star to capture its energy output, a concept first proposed by physicist Freeman Dyson in the 1960s. While the idea of alien megastructures might sound like science fiction, it's grounded in the search for signs of extraterrestrial intelligence, or SETI. Scientists have been scanning the skies for decades, looking for evidence of advanced civilizations, and Tabby's star has become one of the most compelling candidates. However, the search for alien megastructures is not without its challenges. Natural explanations, such as swarms of comets or interstellar debris, could also account for the star's behavior. Despite extensive observations, no definitive evidence of extraterrestrial engineering has been found. Yet, the possibility remains tantalizing. If an alien megastructure were discovered, it would be one of the most profound discoveries in human history, reshaping our understanding of life in the universe. It would suggest that advanced civilizations are capable of engineering on a cosmic scale, harnessing the energy of entire stars. The implications for humanity's future would be equally staggering, offering a glimpse of what we might one day achieve. As we continue to study Tabby's star and other mysterious objects in the cosmos, the search for extraterrestrial engineering remains a thrilling frontier. Could the dimming of Tabby's star be the first clue to uncovering an alien civilization, or is it simply another cosmic mystery waiting to be solved? The answers may lie in the stars, waiting for us to uncover them. Now turning to our 18th theory, we explore the chilling possibility of vacuum decay, a scenario that could spell the end of the universe as we know it. This theory hinges on the idea that our universe exists in a state known as a false vacuum, a seemingly stable but potentially precarious condition. According to quantum field theory, the vacuum of space is not truly empty but filled with energy fields, including the Higgs field, which gives particles their mass. However, scientists speculate that this state might not be the lowest possible energy configuration. If a tiny region of space were to transition to a true vacuum, a state of lower energy, it could trigger a catastrophic chain reaction. This transition would create a bubble of true vacuum that expands at the speed of light, obliterating everything in its path. The laws of physics as we know them would cease to exist within this bubble, rendering all matter and energy unrecognizable. The Higgs field plays a crucial role in this theory, as its stability is what keeps our universe intact. If the Higgs field were to destabilize even for an instant, it could initiate vacuum decay. While this might sound like the plot of a science fiction movie, it's a genuine concern in theoretical physics. The good news is that the likelihood of such an event is incredibly low, given the apparent stability of the universe over billions of years. However, the mere possibility raises profound questions about the fragility of existence. What if a high-energy experiment or a cosmic event were to destabilize the Higgs field? Could humanity inadvertently trigger its own demise? These questions, while unsettling, highlight the delicate balance that governs our universe. Vacuum decay serves as a stark reminder of how much we still have to learn about the fundamental forces that shape reality. As we continue to probe the mysteries of the cosmos, theories like this challenge us to consider not only the origins of the universe but also its potential end. Could the universe be sitting on a knife's edge, one quantum fluctuation away from annihilation? Or is the vacuum of space more stable than we imagine? The answers lie in the intricate interplay of physics and chance, waiting to be uncovered. Now turning to our 19th theory, we delve into the fascinating concept of eternal inflation, a theory that suggests our universe is just one of countless bubble universes in an ever-expanding multiverse. According to this idea, the universe we inhabit is not static but constantly inflating, stretching space itself at an exponential rate. This process is thought to have begun shortly after the Big Bang, driven by a mysterious force known as the inflaton field. As the universe expands, pockets of space can stop inflating and settle into stable states, forming what we perceive as separate bubble universes. Each of these bubbles could have its own unique physical laws and constants, making them vastly different from our own. This means that somewhere out there, an infinite number of universes might exist, each with its own version of reality. The implications of eternal inflation are staggering. It challenges our understanding of the cosmos by suggesting that our universe is just one tiny part of a much larger, perhaps infinite, multiverse. This raises profound questions about the nature of existence. Are there other versions of us living in these bubble universes? Could life exist in forms we can't even imagine? The theory also provides a potential explanation for the fine-tuning of our universe's physical constants. If an infinite number of universes exist, it's statistically inevitable that at least one would have the right conditions for life. However, eternal inflation is not without its challenges. For one, it's difficult to test or observe other bubble universes directly, as they would be separated from us by regions of space that are still inflating. Additionally, the theory relies on the existence of the inflaton field, which has yet to be detected. Despite these uncertainties, eternal inflation remains a compelling framework for understanding the origins and structure of the cosmos. It invites us to rethink our place in the universe and consider the possibility that reality is far more complex and interconnected than we ever imagined. Could the multiverse be the ultimate frontier of exploration, or is it a concept that will forever remain beyond our reach? As we continue to unravel the mysteries of the universe, theories like eternal inflation remind us that the cosmos is full of surprises waiting to be discovered. Now turning to our 20th theory, we explore the intriguing concept of black stars, a radical idea that challenges our traditional understanding of black holes. Unlike the conventional view that black holes contain singularities, points of infinite density where the laws of physics break down, black star theory proposes that some black holes might instead be filled with exotic matter. This exotic matter could prevent the formation of a singularity, creating a stable, ultra-dense object that behaves very differently from what we expect. The idea stems from the possibility that under extreme conditions, matter might transform into a state that resists collapse into a singularity. This could occur if quantum effects or unknown forces counteract the immense gravitational pull at the core of a black hole. If true, black stars would not have event horizons, the boundaries beyond which nothing can escape. Instead, they might emit faint radiation, making them detectable in ways that traditional black holes are not. This theory has profound implications for our understanding of black hole physics. It challenges the long-held assumption that singularities are an inevitable consequence of gravitational collapse. If black stars exist, they could provide new insights into the nature of space-time, gravity, and the behavior of matter under extreme conditions. They might also help resolve some of the paradoxes associated with black holes, such as the information paradox, which questions whether information is truly lost when matter falls into a black hole. However, the black star theory is not without its skeptics. Detecting these objects would be incredibly challenging, as they would resemble black holes in many ways. Additionally, the existence of exotic matter remains speculative, with no direct evidence to support it. Despite these uncertainties, the idea of black stars opens up exciting possibilities for rethinking one of the most mysterious phenomena in the universe. Could black stars be the key to unlocking the secrets of black holes, or are they simply a fascinating theoretical construct? As we continue to probe the depths of space, Theories like this remind us that the cosmos is full of surprises, waiting to challenge our understanding of reality. Now turning to our 21st theory, we delve into the fascinating quest for a unified theory of quantum gravity. This theory represents one of the most significant challenges in modern physics, aiming to bridge the gap between two of the most successful yet seemingly incompatible frameworks, quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles at the smallest scales, where probabilities and uncertainties dominate. On the other hand, general relativity describes the force of gravity as the curvature of spacetime, shaping the motion of planets, stars, and galaxies on cosmic scales. While both theories have been incredibly successful in their respective domains, they break down when applied to extreme conditions, such as those found inside black holes or during the Big Bang. This is where quantum gravity comes in. The goal of quantum gravity is to unify these two theories into a single framework that can describe the universe at all scales, from the tiniest particles to the vastness of spacetime. One of the leading candidates for such a theory is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. Another approach is loop quantum gravity, which suggests that spacetime itself is quantized, composed of discrete loops at the smallest scales. Both theories attempt to reconcile the probabilistic nature of quantum mechanics with the deterministic curvature of spacetime described by general relativity. The implications of a successful quantum gravity theory are profound. It could provide insights into the nature of singularities, the behavior of spacetime at the Planck scale, and even the origins of the universe itself. However, the quest for quantum gravity is far from complete. Experimental evidence remains elusive, as the effects of quantum gravity are expected to manifest only at energy levels far beyond our current technological capabilities. Despite these challenges, the pursuit of quantum gravity continues to inspire physicists worldwide, driven by the hope of uncovering a deeper understanding of the cosmos. Could quantum gravity be the key to unlocking the ultimate secrets of the universe, or will it remain an elusive dream? As we explore this theory, we are reminded that the journey to understand reality is as vast and mysterious as the universe itself. Now turning to our 22nd theory, we explore the intriguing idea that the universe itself might be conscious. This concept, known as the cosmic consciousness theory, suggests that the cosmos is not just a collection of inert matter and energy, but a living, self-aware entity. The roots of this theory stretch back to ancient philosophical traditions, where thinkers like the Greek philosopher Plato and the Hindu Vedantic sages proposed that the universe possesses a form of universal intelligence or consciousness. In more modern times, this idea has been revisited by scientists and philosophers who argue that consciousness might be a fundamental property of the universe, much like space, time, or energy. One of the key proponents of this idea is the physicist and philosopher David Bohm, who suggested that the universe operates as an interconnected whole, with consciousness playing a central role in shaping reality. This theory challenges our conventional understanding of life and intelligence, which typically views consciousness as a product of complex biological systems, such as the human brain. If the universe itself is conscious, it raises profound questions about the nature of existence. Could the cosmos be aware of itself? Does it have intentions or purposes? And if so, what does that mean for our place within it? The cosmic consciousness theory also intersects with quantum mechanics, where the observer effect suggests that the act of observation can influence the behavior of particles. Some interpretations propose that consciousness might be a fundamental force that collapses quantum probabilities into definite states. While this theory remains speculative and lacks empirical evidence, it invites us to reconsider the boundaries between mind and matter, life and the universe. It challenges us to think beyond the limitations of our current scientific frameworks and imagine a cosmos that is not only vast and mysterious but also alive and aware. Could the universe be more than just a stage for life? Could it be a conscious participant in its own unfolding story? As we ponder these questions, we are reminded that the mysteries of the cosmos are as much about the nature of consciousness as they are about the stars and galaxies that fill the night sky. Now turning to our 23rd theory, we delve into the fascinating possibility that our universe may have collided with others, leaving behind observable imprints. This idea, known as the parallel universe collision theory, suggests that our cosmos is not alone but part of a multiverse where multiple universes coexist and occasionally interact. The concept of a multiverse is not new, with theories like bubble universes and quantum branching already proposing the existence of parallel realities. However, the idea of collisions between these universes adds a dramatic twist to the narrative. Scientists have speculated that such collisions could leave behind detectable signatures, such as unusual patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. These patterns, often referred to as bruises or scars, could provide evidence of a cosmic clash between our universe and another. One of the most intriguing pieces of potential evidence comes from the study of the CMB, where researchers have identified anomalies like the cold spot, a region of space that is significantly cooler than its surroundings. Some theorists propose that this could be the result of a collision with a parallel universe, leaving a mark on our own. If true, this would revolutionize our understanding of cosmology, suggesting that our universe is not an isolated entity but part of a vast, interconnected multiverse. The implications of such collisions are profound. They could explain why certain regions of space exhibit unusual gravitational effects, or why the distribution of matter in the universe appears uneven. Moreover, the idea of parallel universes colliding raises questions about the nature of reality itself. Could these collisions create new universes or alter the fundamental laws of physics? And if so, what does that mean for the stability and future of our own cosmos? While the parallel universe collision theory remains speculative, it challenges us to think beyond the boundaries of our observable universe and consider the possibility that we are part of a much larger, more dynamic cosmic tapestry. As we explore these ideas, we are reminded that the universe is full of mysteries waiting to be uncovered, and each discovery brings us closer to understanding the true nature of reality. Now turning to our 24th theory, we explore the incredible phenomenon of neutron star quakes, a cosmic event that releases unimaginable amounts of energy. Neutron stars, the remnants of massive stars that have exploded in supernova, are among the densest objects in the universe. These stars are so compact that a single teaspoon of neutron star material would weigh billions of tons on Earth. But what makes neutron stars even more fascinating is their potential to experience starquakes, violent tremors that ripple across their surfaces. These quakes occur when the crust of a neutron star, which is incredibly rigid due to the immense gravitational forces, suddenly cracks and shifts. When this happens, it releases a burst of energy so powerful that it can be detected across vast distances in space. One of the most intriguing aspects of neutron star quakes is their connection to gamma-ray bursts, some of the most energetic events in the universe. Scientists have theorized that these bursts, which can outshine entire galaxies for a brief moment, might be caused by the massive energy released during a neutron star quake. The idea is that as the star's crust fractures, it triggers a release of magnetic energy stored within the star, producing a gamma-ray burst that travels through space. This theory could help explain some of the mysterious gamma-ray bursts that have puzzled astronomers for decades. Additionally, neutron star quakes might also shed light on other cosmic phenomena, such as fast radio bursts, which are brief but intense pulses of radio waves. Some researchers suggest that these bursts could be linked to the same mechanisms that cause neutron star quakes, providing a unified explanation for these seemingly unrelated events. The study of neutron star quakes not only deepens our understanding of these exotic objects, but also offers insights into the extreme conditions that exist in the universe. By examining the aftermath of these quakes, scientists can learn more about the internal structure of neutron stars and the forces that govern their behavior. As we continue to explore the mysteries of neutron stars, we are reminded of the incredible power and complexity of the cosmos, where even the smallest events can have far-reaching consequences. Now turning to our 25th theory, we delve into the fascinating world of quantum tunneling, a phenomenon that defies our everyday understanding of physics. Quantum tunneling occurs when particles, such as electrons, pass through barriers that, according to classical physics, they shouldn't be able to penetrate. Imagine a ball rolling up a hill. Classical physics tells us that if the ball doesn't have enough energy, it will never make it over the top. But in the quantum realm, particles can sometimes tunnel through the hill, appearing on the other side as if by magic. This strange behavior arises from the probabilistic nature of quantum mechanics, where particles exist as waves of probability rather than definite objects. These waves can extend through barriers, allowing particles to appear on the other side, even if they lack the energy to overcome the barrier in the traditional sense. One of the most significant implications of quantum tunneling is its role in quantum computing. In traditional computers, information is processed using bits, which can be either 0 or 1. Quantum computers, however, use qubits, which can exist in multiple states simultaneously thanks to quantum superposition. Quantum tunneling allows qubits to explore many possible solutions to a problem at once, potentially enabling quantum computers to solve complex problems far more efficiently than classical computers. Beyond computing, quantum tunneling also challenges our understanding of reality itself. It suggests that the universe operates on principles that are fundamentally different from the deterministic laws we observe in our macroscopic world. For instance, quantum tunneling plays a crucial role in nuclear fusion within stars, where protons overcome their mutual repulsion to fuse and release energy. Without tunneling, stars like our Sun wouldn't shine. This phenomenon also has practical applications in modern technology, such as in the operation of tunnel diodes and scanning tunneling microscopes, which allow scientists to observe and manipulate matter at the atomic level. The implications of quantum tunneling extend even further, raising profound questions about the nature of existence. If particles can appear where they seemingly shouldn't, what does that say about the boundaries of reality? Could there be other phenomena in the universe that operate on similar principles waiting to be discovered? As we continue to explore the mysteries of quantum mechanics, we are reminded that the universe is far stranger and more wondrous than we can imagine. Quantum tunneling not only reshapes our understanding of physics, but also opens the door to new technologies and possibilities that could transform our future. Now turning to our 26th theory, we explore the intriguing idea of dark energy stars, a concept that could revolutionize our understanding of stellar phenomena. Unlike traditional stars, which generate energy through nuclear fusion in their cores, dark energy stars are hypothesized to be powered by dark energy, the mysterious force driving the accelerated expansion of the universe. This theory suggests that certain cosmic anomalies, such as unexplained bursts of energy or unusual gravitational effects, could be the result of these enigmatic stars. Dark energy stars would operate on entirely different principles than conventional stars. Instead of fusing hydrogen into helium, they might harness the repulsive force of dark energy to sustain their luminosity and structure. This could explain why some regions of the universe exhibit energy outputs that defy our current models of stellar physics. For instance, certain gamma-ray bursts or gravitational wave signals might originate from the collapse or interaction of dark energy stars, offering a new lens through which to interpret these cosmic events. The existence of dark energy stars could also shed light on the nature of dark energy itself, one of the greatest mysteries in modern cosmology. If dark energy can power stars, it might have far-reaching implications for the life cycle of galaxies and the ultimate fate of the universe. Could dark energy stars be the missing link in our understanding of cosmic evolution? As we continue to probe the depths of space, this theory challenges us to rethink the fundamental processes that govern the cosmos. Dark energy stars not only expand our knowledge of stellar mechanics, but also invite us to consider the possibility of entirely new forms of celestial bodies, waiting to be discovered in the vast expanse of the universe. Now turning to our 27th theory, we delve into the fascinating and mind-bending world of time travel paradoxes. These paradoxes challenge our understanding of cause and effect, raising questions about the very fabric of reality. One of the most famous is the grandfather paradox, which asks what would happen if a time traveler went back in time and prevented their own grandfather from meeting their grandmother. If successful, the time traveler would never be born, making it impossible for them to travel back in time in the first place. This creates a logical loop that seems impossible to resolve. Another well-known paradox is the bootstrap paradox, where an object or piece of information is sent back in time and becomes the cause of itself. For example, imagine a person who travels back in time and gives Beethoven his own sheet music, which Beethoven then publishes as his own work. The question arises, who actually composed the music? These paradoxes highlight the complexities and contradictions that arise when we consider the possibility of time travel. They also force us to confront the limitations of our current understanding of physics, particularly when it comes to the nature of time and causality. Could time travel ever be possible without creating these paradoxes? Some theories suggest that the universe might have built-in mechanisms to prevent such contradictions, such as the idea of parallel timelines or the many worlds interpretation of quantum mechanics. According to these ideas, any changes made by a time traveler would create a new, alternate reality, leaving the original timeline untouched. While these solutions offer intriguing possibilities, they also raise new questions about the nature of reality and our place within it. Time travel paradoxes not only challenge our scientific theories, but also invite us to explore the philosophical implications of altering the past. What does it mean for free will if the past can be changed? And how do we define identity if our actions in the past could erase our very existence? As we continue to explore the mysteries of time, these paradoxes remind us that the universe is far more complex and enigmatic than we can imagine. Now turning to our 28th theory, we explore the intriguing concept of cosmic strings, one-dimensional defects in the fabric of space-time. Imagine the universe as a vast, intricate tapestry and cosmic strings as tiny, thread-like imperfections woven into its structure. These strings are thought to have formed in the early moments of the universe, during a phase transition when the cosmos cooled and expanded rapidly. Unlike black holes or stars, cosmic strings are incredibly thin but possess immense density, stretching across unimaginable distances. They are essentially cracks in space-time, remnants of the universe's fiery birth, and could hold the key to understanding some of the most profound mysteries of cosmology. One of the most fascinating aspects of cosmic strings is their potential role in the formation of galaxies and large-scale structures in the universe. As these strings move through space-time, they create ripples and disturbances, much like a stone dropped into a pond. These ripples could have acted as seeds for the clumping of matter, eventually leading to the formation of galaxies, galaxy clusters, and the cosmic web we observe today. Some scientists even suggest that cosmic strings could explain certain anomalies in the cosmic microwave background, the faint afterglow of the Big Bang. While cosmic strings remain theoretical, their existence could provide a bridge between the quantum world and the vast scales of the cosmos. If detected, they would offer a glimpse into the universe's earliest moments and help us unravel the forces that shaped its evolution. The search for cosmic strings continues, with astronomers scanning the skies for telltale signs. such as distortions in the light from distant galaxies or unusual gravitational wave patterns. As we ponder the possibility of these space-time threads, we are reminded once again of the universe's boundless complexity and the endless mysteries waiting to be uncovered. Could cosmic strings be the missing link in our understanding of the cosmos? And what other secrets might they reveal about the origins and fate of the universe? These questions drive us to look deeper into the fabric of reality, where even the smallest imperfections might hold the answers to the grandest questions. Now turning to our 29th theory, we delve into the mind-bending concept of the quantum foam, a term that paints a picture of space-time as a frothy, ever-fluctuating sea at the tiniest scales imaginable. Imagine zooming in on the fabric of the universe so far that the smooth, continuous space-time we perceive dissolves into a chaotic, bubbling foam. This is the quantum foam, a theoretical framework that suggests space-time is not the serene, unbroken expanse we often envision, but rather a turbulent, dynamic landscape at the quantum level. At these infinitesimal scales, particles and energy pop in and out of existence in a frenzy of activity, creating a frothy texture that defies our everyday understanding of reality. This idea arises from the principles of quantum mechanics, which tell us that at the smallest levels, the universe is governed by uncertainty and unpredictability. The quantum foam represents the ultimate manifestation of this uncertainty, where spacetime itself becomes a seething, fluctuating entity. One of the most profound implications of the quantum foam theory is its challenge to our classical notions of space and time. In this frothy realm, the very concepts of distance and duration lose their meaning as spacetime becomes a chaotic, ever-changing medium. This has significant consequences for our understanding of the universe, particularly when it comes to reconciling quantum mechanics with general relativity. The quantum foam suggests that the smooth, curved spacetime described by Einstein's theory is merely an approximation, a large-scale average of the chaotic, fluctuating reality at the quantum level. Some scientists even speculate that the quantum foam could hold the key to understanding the nature of black holes and the singularity at their cores. If spacetime is inherently frothy and unstable at the smallest scales, it might provide a way to avoid the infinite densities predicted by classical physics, offering a potential resolution to the mysteries of singularities. Additionally, the quantum foam could have implications for the nature of reality itself, suggesting that the universe is far more dynamic and unpredictable than we ever imagined. As we explore this theory, we are reminded once again of the universe's capacity to surprise and challenge us, pushing the boundaries of our understanding and inviting us to rethink the very fabric of reality. Could the quantum foam be the key to unlocking the secrets of the quantum world? And what might it reveal about the true nature of spacetime and existence? These questions drive us to probe deeper into the mysteries of the cosmos, where even the smallest fluctuations might hold the answers to the grandest questions. Now turning to our 30th theory, we explore the startling concept of the black hole firewall, a hypothesis that turns our understanding of black holes on its head. According to this theory, the event horizon of a black hole, the point of no return, might not be the smooth, uneventful boundary we once thought. Instead, it could be a blazing wall of energy, a firewall that incinerates anything that crosses it. This idea emerged as a potential solution to the black hole information paradox, which questions whether information about matter falling into a black hole is lost forever or somehow preserved. The firewall theory suggests that the intense gravitational forces at the event horizon create a region of extreme energy, effectively destroying anything that enters. This challenges the traditional view of black holes, where the event horizon is seen as a calm, invisible threshold. If firewalls exist, they would fundamentally alter our understanding of how black holes interact with the universe. For instance, the idea of an astronaut crossing the event horizon unharmed, as predicted by general relativity, would no longer hold true. Instead, they would encounter a catastrophic burst of energy, obliterating them instantly. This raises profound questions about the nature of space-time and the laws of physics. How can such a firewall exist without violating the principles of quantum mechanics and relativity? And what does this mean for the preservation of information in the universe? Some physicists argue that the firewall theory highlights a deep incompatibility between quantum mechanics and general relativity, two pillars of modern physics. Others see it as a call to rethink our understanding of black holes and the fabric of reality itself. As we grapple with these questions, the black hole firewall theory reminds us that even the most well-established ideas in science are open to challenge. Could firewalls be the key to resolving the information paradox, or do they point to an even deeper mystery waiting to be uncovered? These questions drive us to continue exploring the enigmatic nature of black holes, where the answers might reshape our understanding of the cosmos. Now turning to our 31st theory, we delve into the fascinating concept of exotic matter, a hypothetical substance that defies the usual rules of physics. Unlike ordinary matter, exotic matter possesses negative energy density, meaning it can exert a repulsive gravitational force. This bizarre property makes it a key ingredient in some of the most speculative and exciting ideas in theoretical physics, such as wormholes and warp drives. Wormholes, often depicted in science fiction as shortcuts through space-time, would require exotic matter to remain stable and traversable. Without it, the intense gravitational forces would cause the wormhole to collapse instantly. Similarly, warp drives, which could theoretically allow faster-than-light travel by bending space-time, rely on exotic matter to create the necessary distortions. The idea of exotic matter challenges our understanding of energy and gravity, suggesting that the universe might contain forms of matter we have yet to discover. While exotic matter remains purely theoretical, its potential applications could revolutionize space travel and our exploration of the cosmos. Imagine being able to traverse vast distances in an instant or visit distant galaxies within a human lifetime. These possibilities hinge on the existence and manipulation of exotic matter, making it one of the most intriguing and elusive concepts in modern physics. As we continue to explore the boundaries of our knowledge, the search for exotic matter reminds us that the universe is full of surprises waiting to be uncovered. Could this strange substance hold the key to unlocking the secrets of space-time, or is it merely a tantalizing glimpse of what lies beyond our current understanding? These questions drive us to push the limits of science, seeking answers that could transform our place in the cosmos. Now turning to our 32nd theory, we explore the intriguing concept of quantum consciousness, a hypothesis that suggests consciousness itself may arise from quantum processes within the brain. This theory challenges the traditional view that consciousness is purely a product of classical physics and neural activity. Instead, it proposes that the strange and unpredictable nature of quantum mechanics, such as superposition and entanglement, might play a fundamental role in how we experience thoughts, awareness, and reality. One of the key proponents of this idea is physicist Roger Penrose, who, along with anesthesiologist Stuart Hameroff, developed the orchestrated objective reduction theory. This theory suggests that quantum vibrations in microtubules, tiny structures within brain cells, could be the foundation of consciousness. If true, this would mean that our minds operate on a quantum level, blurring the line between the physical and the metaphysical. The implications of quantum consciousness are profound. It could explain phenomena like intuition, creativity, and even the nature of free will, suggesting that our decisions might be influenced by quantum randomness rather than purely deterministic processes. Furthermore, it raises questions about the nature of reality itself. If consciousness is rooted in quantum mechanics, does that mean our perception of the universe is inherently tied to its quantum fabric? Could this explain why the act of observation seems to affect quantum systems, as seen in the famous double-slit experiment? While the quantum consciousness theory remains highly speculative and controversial, it opens up exciting possibilities for understanding the mind and its connection to the cosmos. Could our brains be quantum computers processing information in ways we are only beginning to comprehend? And if so, what does that mean for the future of artificial intelligence and our understanding of life itself? These questions push the boundaries of science and philosophy, inviting us to rethink what it means to be conscious in a quantum universe. Now turning to our 33rd theory, we delve into the cosmic inflation theory, a groundbreaking idea that explains how the universe underwent an exponential expansion in the earliest moments of its existence. This theory suggests that just a fraction of a second after the Big Bang, the universe expanded faster than the speed of light, growing from a tiny speck to an enormous size in an incredibly short time. This rapid expansion helps explain why the universe appears so uniform and why it lacks certain features like magnetic monopoles that would otherwise be expected. The evidence for cosmic inflation comes from observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Tiny fluctuations in this radiation match the predictions of inflation, providing strong support for the theory. Additionally, inflation explains the large-scale structure of the universe, such as the distribution of galaxies and galaxy clusters, which align with the patterns expected from such an expansion. The implications of cosmic inflation are profound. It not only supports the Big Bang theory, but also suggests that our universe is just one of many in a vast multiverse. If inflation occurred once, it could have happened countless times, creating bubble universes with different physical laws. This raises fascinating questions about the nature of reality and our place within it. Could there be other universes out there, each with its own unique properties? And if so, what does that mean for our understanding of existence? While cosmic inflation remains a theoretical framework, it has become a cornerstone of modern cosmology, offering a compelling explanation for the origins and structure of our universe. As we continue to explore the cosmos, this theory challenges us to rethink the very fabric of reality and the forces that shaped it. Now turning to our 34th theory, we explore the intriguing connection between black holes and entropy, a concept that challenges our understanding of thermodynamics and information. Black holes, often thought of as cosmic vacuum cleaners, are not just regions of immense gravity, but also objects with a surprising link to the second law of thermodynamics. This law states that entropy, a measure of disorder, always increases in a closed system. But how does this apply to black holes? In the 1970s, physicist Jacob Bekenstein proposed that black holes possess entropy, which is directly related to the surface area of their event horizons. This idea was revolutionary because it suggested that black holes are not just simple, featureless objects, but rather complex systems with a hidden structure. Stephen Hawking later expanded on this, showing that black holes emit radiation, now known as Hawking radiation, which causes them to lose mass and eventually evaporate. This discovery linked black holes to thermodynamics even further, as it implied that black holes have temperature and can exchange energy with their surroundings. The connection between black holes and entropy raises profound questions about the nature of information. According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this principle by swallowing matter and radiation, seemingly erasing information from the universe. This contradiction, known as the black hole information paradox, remains one of the greatest unsolved problems in physics. If black holes do preserve information, where and how is it stored? Some theories suggest that information might be encoded on the event horizon or even in the Hawking radiation itself. others propose that black holes might be gateways to other universes, carrying information away from our own. The black hole entropy theory not only challenges our understanding of thermodynamics, but also forces us to rethink the fundamental nature of reality. As we continue to study these enigmatic objects, we may uncover new insights into the laws that govern the universe and the mysterious interplay between gravity, quantum mechanics, and information. What secrets do black holes hold, and how might they reshape our understanding of existence itself? Now turning to our 35th theory, we delve into the mind-bending concept of quantum superposition, a cornerstone of quantum mechanics that challenges our everyday understanding of reality. At its core, quantum superposition is the idea that particles, such as electrons or photons, can exist in multiple states at once until they are observed or measured. Imagine flipping a coin. Instead of landing on heads or tails, it somehow remains in a state of being both heads and tails simultaneously. This bizarre phenomenon was famously illustrated by Erwin Schrödinger's thought experiment involving a cat that is both alive and dead until observed. While this seems impossible in our macroscopic world, it's a fundamental truth in the quantum realm. Quantum superposition is not just a theoretical curiosity. It has profound implications for the future of technology, particularly in the field of quantum computing. Unlike classical computers, which process information in binary bits, zeros and ones, quantum computers use qubits, which can exist in a superposition of both states at the same time. This allows quantum computers to perform complex calculations at speeds unimaginable with traditional technology, potentially revolutionizing fields like cryptography, medicine, and artificial intelligence. But the implications of quantum superposition go far beyond computing. It forces us to confront deep questions about the nature of reality itself. If particles can exist in multiple states until observed, does that mean reality is not fixed until we interact with it? Some interpretations of quantum mechanics suggest that the act of observation collapses the superposition, bringing one state into existence. Others propose that every possible outcome exists in parallel universes, as suggested by the many worlds interpretation. Quantum superposition challenges our intuitive understanding of cause and effect, time, and even the nature of existence. It blurs the line between the observer and the observed, suggesting that consciousness might play a role in shaping reality. As we continue to explore this strange and fascinating phenomenon, we may uncover new insights into the fabric of the universe and our place within it. What does it mean for reality to be so fluid, and how might this knowledge transform our understanding of the cosmos? Now turning to our 36th theory, we explore the intriguing possibility of life forms based on dark matter. This idea challenges everything we know about biology and the search for extraterrestrial life. Dark matter, which makes up about 27% of the universe, is invisible and does not interact with light or electromagnetic forces, making it undetectable by conventional means. Yet, its gravitational effects are undeniable, shaping the structure of galaxies and the cosmos itself. But what if dark matter isn't just a mysterious cosmic ingredient? What if it could harbor life? The concept of dark matter life suggests that organisms could exist in forms entirely different from the carbon-based life we know. These hypothetical beings would not rely on the same chemical processes as life on Earth. Instead, they might interact through forces we have yet to understand, thriving in environments where conventional life could not survive. This theory forces us to rethink the very definition of life. If life can exist without the building blocks we consider essential, such as water, oxygen, or DNA, then our search for extraterrestrial life may be far too narrow. We might be overlooking entire ecosystems that operate on entirely different principles. The implications for astrobiology are profound. If dark matter life exists, it could be hiding in plain sight, undetectable by our current instruments. This raises questions about how we design missions to search for life beyond Earth. Should we be looking for biosignatures that go beyond the familiar? Could dark matter life be communicating or evolving in ways we cannot yet comprehend? This theory also challenges our understanding of the universe's diversity. If life can emerge in such radically different forms, the cosmos might be teeming with life in ways we have yet to imagine. As we continue to probe the mysteries of dark matter, we may uncover clues that reshape our understanding of biology, existence, and our place in the universe. What if the search for life has only just begun, and the most extraordinary discoveries are still waiting in the shadows? Now turning to our 37th theory, we delve into the enigmatic world of cosmic ray anomalies. These high-energy particles traveling at nearly the speed of light bombard Earth from all directions, yet their origins remain one of the greatest mysteries in astrophysics. Cosmic rays are not rays at all, but rather charged particles, mostly protons and atomic nuclei, that carry immense amounts of energy. Some of these particles have energies millions of times greater than what our most powerful particle accelerators can produce. But where do they come from? The answer is far from clear. While some cosmic rays are thought to originate from supernova, the most energetic ones defy explanation. These ultra-high-energy cosmic rays are so powerful that they should not exist according to our current understanding of physics. Their energy levels are so extreme that they should lose momentum as they travel through the cosmic microwave background radiation, yet they reach Earth intact. This paradox has led scientists to propose some extraordinary possibilities. Could these particles come from supermassive black holes at the centers of galaxies? Or perhaps from the decay of exotic, super-heavy particles left over from the Big Bang? Some even speculate that they might be evidence of undiscovered physics, such as new dimensions or forces beyond the standard model. The implications of solving this mystery are profound. Understanding the origins of these cosmic rays could shed light on the most violent and energetic processes in the universe, from the birth of galaxies to the nature of dark matter. It could also reveal new physics that challenges our fundamental understanding of the cosmos. For now, these high-energy particles remain a tantalizing puzzle, reminding us that the universe still holds secrets we have yet to uncover. As we continue to study these cosmic anomalies, we may find ourselves rewriting the laws of physics and uncovering truths that reshape our understanding of reality itself. Now turning to our 38th theory, we explore the fascinating concept of quantum decoherence. In the strange world of quantum mechanics, particles can exist in multiple states simultaneously, a phenomenon known as superposition. However, when these particles interact with their environment, something peculiar happens. They lose their quantum coherence and begin to behave like classical objects. This process is called quantum decoherence, and it plays a crucial role in explaining why the quantum world appears so different from the everyday world we experience. At its core, quantum decoherence occurs because interactions with the environment cause the delicate quantum states to become entangled with countless other particles. This entanglement effectively washes out the quantum effects, making the system appear classical. For example, imagine a quantum particle in a superposition of two states. When it interacts with its surroundings, the information about its superposition spreads out into the environment, making it impossible to observe the quantum behavior directly. This process helps explain why we don't see macroscopic objects like chairs or tables. Existing in superpositions, they are constantly interacting with their environment, causing decoherence to occur almost instantly. But quantum decoherence isn't just a quirk of quantum mechanics. It has profound implications for one of the most debated problems in physics, the measurement problem. The measurement problem asks why quantum systems appear to choose a definite state when observed, even though they exist in superpositions before measurement. Decoherence provides a partial answer by showing how interactions with the environment can make quantum superpositions effectively disappear, leading to the appearance of classical behavior. However, it doesn't fully solve the problem, as it doesn't explain why a specific outcome is observed rather than another. This has led some physicists to propose that decoherence must be combined with other interpretations of quantum mechanics, such as the many worlds interpretation or objective collapse theories, to fully address the measurement problem. The implications of quantum decoherence extend far beyond theoretical physics. It has practical applications in the development of quantum computers, where maintaining coherence is essential for performing complex calculations. If decoherence can be controlled or minimized, it could pave the way for revolutionary advancements in technology, from ultra-secure communication to solving problems that are currently beyond the reach of classical computers. As we continue to unravel the mysteries of quantum decoherence, we are reminded of the delicate balance between the quantum and classical worlds. This theory not only challenges our understanding of reality, but also opens the door to new possibilities in science and technology. With each discovery, we come closer to bridging the gap between the strange, counterintuitive quantum realm and the familiar world we inhabit. Now turning to our 39th theory, we delve into the mind-bending concept of black hole time dilation. Near the immense gravitational pull of a black hole, time itself behaves in ways that defy our everyday experience. This phenomenon, known as time dilation, occurs because the extreme gravity of a black hole warps spacetime to such an extent that time slows down dramatically for an observer close to the event horizon compared to someone far away. Imagine you are watching a clock fall toward a black hole. As it gets closer to the event horizon, the point of no return, the clock would appear to tick slower and slower from your perspective. For the clock itself, time would pass normally, but for you, it would seem to take an eternity for the clock to reach the horizon. This effect, predicted by Einstein's theory of general relativity, has been confirmed by observations of objects near massive cosmic bodies, though black holes take it to the extreme. The implications of black hole time dilation are profound, especially when it comes to the concept of time travel. If someone were to venture close to a black hole and then return to a distant observer, they would find that much more time has passed for the observer than for themselves. This means that, in theory, black holes could serve as natural time machines, allowing for travel into the distant future. However, the practical challenges of surviving such a journey, including the intense tidal forces and radiation near a black hole, make this idea more of a thought experiment than a feasible reality, at least for now. Beyond time travel, black hole time dilation also challenges our understanding of spacetime itself. It reveals how gravity doesn't just bend space but also stretches and distorts time, creating a dynamic interplay between the two. This has led physicists to explore deeper questions about the nature of reality, such as whether time is truly a fundamental aspect of the universe or merely an emergent property of spacetime. As we continue to study black holes and their effects on time, we are reminded of how much we still have to learn about the cosmos. Black hole time dilation not only pushes the boundaries of our scientific knowledge, but also sparks our imagination, inviting us to ponder the mysteries of time, gravity, and the very fabric of existence. With each discovery, we come closer to unraveling the secrets of these enigmatic cosmic giants and their role in shaping the universe. Now turning to our 40th theory, we explore the fascinating possibility of detecting quantum-scale gravitational waves. These tiny ripples in spacetime, predicted by quantum mechanics, could hold the key to unlocking new frontiers in physics. Unlike the large-scale gravitational waves detected by observatories like LIGO, which are produced by massive cosmic events like black hole mergers, quantum gravity waves would be generated by the smallest particles and interactions in the universe. The idea of quantum gravity waves stems from the quest to unify quantum mechanics and general relativity. two of the most successful but seemingly incompatible theories in physics. While general relativity describes gravity as the curvature of spacetime caused by massive objects, quantum mechanics governs the behavior of particles at the smallest scales. Quantum gravity waves would represent a bridge between these two realms, offering a glimpse into how gravity operates at the quantum level. Detecting these waves is no small feat. They would be incredibly faint, requiring highly sensitive instruments far beyond our current technological capabilities. However, if scientists could observe them, it would revolutionize our understanding of the universe. Quantum gravity waves could reveal the existence of new particles, shed light on the nature of dark matter and dark energy, and even provide clues about the early moments of the Big Bang. One of the most exciting possibilities is that quantum gravity waves could help us uncover the elusive theory of quantum gravity, a framework that would reconcile the quantum world with the force of gravity. This would not only solve one of the greatest puzzles in modern physics, but also open the door to new technologies and a deeper understanding of the cosmos. As we continue to push the boundaries of science, the search for quantum gravity waves reminds us of the vast mysteries that still await discovery. These tiny ripples in space-time may seem insignificant, but they could hold the answers to some of the most profound questions about the universe and our place within it. With each step forward, we inch closer to unraveling the secrets of quantum gravity and the fundamental nature of reality itself. Now turning to our 41st theory, we delve into the cosmic neutrino background, a faint echo of the Big Bang that permeates the universe. Neutrinos are nearly massless, neutral particles that interact so weakly with matter that they can pass through entire planets without a trace. Billions of these ghostly particles are streaming through you right now, completely unnoticed. But in the early universe, neutrinos played a crucial role, and their remnants still linger as a cosmic fossil. The cosmic neutrino background is thought to have formed just 1 second after the Big Bang, when the universe was a seething soup of particles and energy. As the universe expanded and cooled, neutrinos decoupled from matter, traveling freely through space ever since. This background is similar to the cosmic microwave background, the afterglow of the Big Bang, but it is far more elusive. While the cosmic microwave background was detected in the 1960s, the cosmic neutrino background remains undetected, hidden by its incredibly weak interactions. Detecting this background would be a monumental achievement for cosmology and particle physics. It would provide a direct snapshot of the universe just moments after its birth, offering insights into the conditions that shape the cosmos. By studying the cosmic neutrino background, scientists could test theories about the early universe, such as inflation, and better understand the behavior of neutrinos themselves. These particles are still full of mysteries, including their exact masses and whether they are their own antiparticles. The implications of this theory extend beyond cosmology. Neutrinos are a key piece of the puzzle in understanding the fundamental forces and particles that make up the universe. Their behavior could shed light on the asymmetry between matter and antimatter, explaining why the universe is dominated by matter today. Additionally, the cosmic neutrino background could help refine our understanding of dark matter and dark energy, the invisible forces driving the universe's expansion. As we continue to explore the cosmos, the search for the cosmic neutrino background reminds us of the profound connections between the smallest particles and the largest structures in the universe. These ghostly relics of the Big Bang may hold the keys to unlocking some of the deepest mysteries of existence, bridging the gap between the quantum world and the vast expanse of space. With each discovery, we come closer to understanding the intricate tapestry of the cosmos and our place within it. Now turning to our 42nd theory, we explore the fascinating idea that quantum entanglement could be the key to time travel. Quantum entanglement is a phenomenon where two particles become linked, no matter how far apart they are. changes to one particle instantly affect the other, even if they are light years apart. This strange connection, which Albert Einstein famously called spooky action at a distance, has long puzzled scientists, but could it also hold the secret to traveling through time? The theory suggests that entangled particles might create a bridge between different points in time. If we could manipulate these particles, we might be able to send information or even matter backward or forward in time. Imagine sending a message to your past self or glimpsing the future through the lens of quantum physics. While this sounds like science fiction, some physicists believe it could be possible thanks to the bizarre rules of quantum mechanics. However, the challenges are immense. For one, maintaining entanglement over long distances or periods of time is incredibly difficult. Any interaction with the environment can break the delicate link between particles. Additionally, the idea of time travel raises paradoxes, such as the famous grandfather paradox, where changing the past could create contradictions. These paradoxes make the concept of time travel through entanglement both thrilling and deeply problematic. The implications of this theory are profound. If quantum entanglement could be harnessed for time travel, it would revolutionize our understanding of physics and the nature of reality itself. It could provide new insights into the flow of time, the structure of space-time, and the fundamental laws of the universe. Moreover, it could open up possibilities for communication across time, allowing us to send information to future generations or even receive messages from the past. As we continue to unravel the mysteries of quantum entanglement, the idea of time travel remains a tantalizing possibility. While the challenges are daunting, the potential rewards are equally extraordinary. This theory reminds us that the universe is far stranger and more interconnected than we can imagine, and that the boundaries of time and space may not be as rigid as they seem. With each discovery, we edge closer to understanding whether the secrets of time travel lie hidden in the quantum realm. Now turning to our 43rd theory, we delve into the intriguing possibility of retrieving information from black holes. This idea challenges one of the most perplexing problems in modern physics, the black hole information paradox. According to classical physics, once something crosses the event horizon of a black hole, it is lost forever, including all the information it carries. This seems to violate a fundamental principle of quantum mechanics, which states that information cannot be destroyed. So, where does the information go? The black hole information retrieval theory suggests that information might not be lost after all. Instead, it could be encoded in some form on the surface of the black hole, or even radiated back into the universe through a process known as Hawking radiation. Stephen Hawking proposed that black holes emit radiation due to quantum effects near the event horizon, slowly losing mass over time. This radiation might carry traces of the information that fell into the black hole, effectively allowing it to escape. However, the process is far from straightforward. The information, if retrievable, would be scrambled and incredibly difficult to decode. It would require a deep understanding of quantum gravity, a theory that unites quantum mechanics and general relativity, which remains one of the greatest unsolved problems in physics. Some scientists propose that the information might be stored in the form of quantum hair, subtle imprints on the black hole's surface that encode the details of everything that has fallen in. The implications of this theory are profound. If information can indeed be retrieved from black holes, it would resolve the information paradox and provide a major breakthrough in our understanding of the universe. It would also suggest that black holes are not the ultimate cosmic trash cans, but rather complex systems that preserve information in ways we are only beginning to comprehend. This could reshape our understanding of space-time, quantum mechanics, and the very nature of reality. As we continue to explore the mysteries of black holes, the idea of retrieving information remains a tantalizing possibility. While the challenges are immense, the potential rewards are equally extraordinary. This theory reminds us that even the most enigmatic objects in the universe may hold the keys to unlocking its deepest secrets. With each discovery, we edge closer to understanding whether the information we thought was lost forever might still be within our reach. Now turning to our 44th theory, we explore the fascinating concept of quantum vacuum fluctuations. This theory suggests that even in the complete emptiness of a vacuum, particles can spontaneously pop into and out of existence. At first glance, this idea seems to defy common sense. How can something come from nothing? Yet, this phenomenon is a direct consequence of the principles of quantum mechanics. According to quantum theory, empty space is not truly empty. Instead, it is a seething, dynamic arena where pairs of particles and antiparticles momentarily appear and then annihilate each other. These fleeting particles are known as virtual particles, and their existence is a result of the uncertainty principle, which allows energy to fluctuate briefly on the smallest scales. These fluctuations are so tiny and short-lived that they are nearly impossible to detect directly, but their effects can be observed indirectly through phenomena like the Casimir effect, where two uncharged metal plates placed close together experience an attractive force due to the quantum vacuum between them. The implications of quantum vacuum fluctuations are profound. They challenge our understanding of what it means for space to be empty, and suggest that the fabric of reality is far more dynamic and unpredictable than we once thought. This theory also has significant implications for our understanding of energy. If particles can appear and disappear in a vacuum, it implies that energy is not always conserved in the way classical physics suggests. Instead, energy can be borrowed from the vacuum as long as it is returned almost immediately. This idea has led to some mind-bending possibilities, such as the concept of zero-point energy, the lowest possible energy that a quantum system can have. Some scientists speculate that if we could harness this energy, it could provide an almost limitless source of power. However, the practical challenges of doing so are immense, as the energy fluctuations are incredibly small and difficult to manipulate. Quantum vacuum fluctuations also play a crucial role in our understanding of the early universe. During the Big Bang, these fluctuations may have been amplified, leading to the formation of the large-scale structures we see in the cosmos today, such as galaxies and galaxy clusters. In this way, the tiny, fleeting particles that pop in and out of existence in the vacuum may have had a profound impact on the evolution of the universe. As we continue to explore the quantum realm, the theory of vacuum fluctuations reminds us that even the emptiest spaces are teeming with activity. It challenges us to rethink our assumptions about the nature of reality and energy, and it opens up new possibilities for understanding the universe at its most fundamental level. With each discovery, we come closer to unraveling the mysteries of the quantum vacuum and its role in shaping the cosmos. Now turning to our 45th theory, we delve into the intriguing role of cosmic magnetic fields in shaping the universe. While we often think of gravity as the dominant force in the cosmos, magnetic fields also play a crucial role in influencing the structure and evolution of galaxies, stars, and even the vast intergalactic medium. These invisible forces, generated by the movement of charged particles, weave through the fabric of space, leaving their mark on the cosmic landscape. Magnetic fields are found almost everywhere in the universe, from the smallest scales of planetary systems to the largest structures like galaxy clusters. They are created by the motion of charged particles such as electrons and protons, often driven by processes like star formation, supernova explosions, and the rotation of galaxies. Once generated, these fields can stretch across vast distances, shaping the behavior of gas, dust, and plasma in ways that gravity alone cannot explain. One of the most fascinating aspects of cosmic magnetic fields is their influence on galaxy formation. As clouds of gas and dust collapse under gravity to form stars and galaxies, magnetic fields can channel and direct the flow of material, creating intricate patterns and structures. For example, magnetic fields can help regulate the rate at which gas collapses into stars, preventing it from collapsing too quickly and allowing galaxies to form in a more orderly fashion. They also play a role in launching powerful jets of particles from the centers of galaxies, driven by supermassive black holes, which can impact the surrounding environment and even trigger new star formation. On larger scales, magnetic fields are thought to influence the evolution of galaxy clusters, the largest gravitationally bound structures in the universe. These fields can affect the motion of hot gas within clusters, shaping the distribution of matter and energy. They may also play a role in the acceleration of cosmic rays, high-energy particles that travel through space at nearly the speed of light. The interaction between magnetic fields and cosmic rays is a key area of research, as it helps us understand the origins of these mysterious particles and their impact on the universe. The study of cosmic magnetic fields also provides insights into the early universe. While the exact origins of these fields remain a mystery, some theories suggest they may have been generated during the inflationary period shortly after the Big Bang. Others propose that they emerged later as the first stars and galaxies formed. By studying the strength and orientation of magnetic fields in distant galaxies and the cosmic microwave background, scientists hope to uncover clues about their origins and evolution over billions of years. As we continue to explore the cosmos, the role of magnetic fields reminds us that the universe is shaped by a complex interplay of forces. From the birth of stars to the dynamics of galaxy clusters, these invisible threads weave through the fabric of space, influencing the evolution of the cosmos in ways we are only beginning to understand. With each discovery, we gain a deeper appreciation for the intricate and dynamic nature of the universe and the magnetic fields that help shape its destiny. Now turning to our 46th theory, we explore the fascinating concept of quantum wormholes and their potential to revolutionize our understanding of space, time, and interstellar travel. Wormholes, often depicted in science fiction as shortcuts through the fabric of space-time, are theoretical passages that could connect distant points in the universe or even different universes altogether. While they remain speculative, the idea of creating wormholes using the principles of quantum mechanics opens up mind-bending possibilities for the future of space exploration and time travel. At the heart of quantum wormhole theory lies the strange and counterintuitive nature of quantum mechanics. In the quantum realm, particles can exist in multiple states simultaneously, tunnel through barriers, and become entangled across vast distances. These phenomena suggest that spacetime itself might have a more flexible and dynamic structure than we once thought. Some physicists propose that under the right conditions, quantum effects could stabilize a wormhole, preventing it from collapsing and making it traversable. One of the key challenges in creating a quantum wormhole is the need for exotic matter or negative energy. Exotic matter, with its unusual properties, could theoretically counteract the immense gravitational forces that would otherwise crush a wormhole. While such matter has not been observed in nature, its existence is not ruled out by the laws of physics. If scientists could harness or create exotic matter, it might be possible to construct a stable wormhole capable of transporting matter or information across vast cosmic distances. The implications of quantum wormholes for interstellar travel are staggering. A traversable wormhole could serve as a cosmic shortcut, allowing spacecraft to bypass the limitations of light-speed travel and reach distant star systems in a fraction of the time. This would not only make interstellar exploration feasible, but could also enable the colonization of other planets and the search for extraterrestrial life. Imagine stepping through a wormhole and emerging in a galaxy millions of light-years away, all within moments. Beyond space travel, quantum wormholes also raise intriguing possibilities for time travel. Some theories suggest that a wormhole could connect not only distant points in space but also different points in time. By manipulating the ends of a wormhole, it might be possible to create a time machine allowing travel to the past or future. While this idea remains highly speculative, it challenges our understanding of causality and the nature of time itself. The study of quantum wormholes also intersects with other cutting-edge areas of physics, such as quantum gravity and string theory. These fields seek to unify the laws of quantum mechanics and general relativity, providing a deeper understanding of the fundamental nature of space-time. If wormholes exist, they could offer a unique window into the quantum structure of the universe and help resolve some of the most profound mysteries in physics. As we continue to explore the frontiers of science, the idea of quantum wormholes reminds us that the universe is far stranger and more wondrous than we can imagine. While the practical realization of wormholes remains a distant dream, their theoretical exploration pushes the boundaries of human knowledge and inspires us to envision a future where the stars are within reach and time itself becomes a frontier to explore. With each discovery, we come closer to unraveling the secrets of the cosmos and the quantum threads that might one day connect us to the farthest reaches of space and time. Now turning to our 47th theory, we delve into the intriguing concept of the black hole quantum hair theory, a hypothesis that challenges our understanding of black holes and the information paradox. For decades, black holes have been thought of as simple objects defined only by their mass, charge, and spin. This idea, known as the no-hair theorem, suggests that black holes are essentially bald with no additional distinguishing features. However, the black hole quantum hair theory proposes that black holes might not be so featureless after all. Instead, they could possess quantum hair, subtle imprints or patterns encoded in their quantum states that carry information about the matter that fell into them. This theory emerges from the ongoing debate over the black hole information paradox, a problem that pits quantum mechanics against general relativity. According to quantum mechanics, information about the state of a system can never be completely lost. Yet, when matter falls into a black hole, it appears to vanish, leaving no trace of its original state. This contradiction has puzzled physicists for decades, with Stephen Hawking famously suggesting that information might be irretrievably lost, a notion that violates the principles of quantum theory. The black hole quantum hair theory offers a potential resolution by suggesting that information is not lost but instead encoded in the quantum structure of the black hole itself. The idea of quantum hair stems from the notion that black holes are not entirely smooth and featureless. Instead, their event horizons might be imprinted with faint quantum fluctuations, like tiny ripples or patterns, that preserve information about the matter that formed them. These quantum imprints could act as a kind of hair, subtly encoding the history of the black hole in a way that is consistent with the laws of quantum mechanics. If true, this would mean that black holes are far more complex than previously thought, with their quantum states holding the key to resolving the information paradox. The implications of this theory are profound. If black holes do have quantum hair, it would mean that information is not lost but instead transformed and preserved in a way that we are only beginning to understand. This could provide a crucial link between quantum mechanics and general relativity, two pillars of modern physics that have so far resisted unification. By studying the quantum properties of black holes, scientists might uncover new insights into the nature of spacetime, gravity, and the fundamental laws that govern the universe. Moreover, the black hole quantum hair theory could have practical implications for our understanding of black hole evaporation. According to Hawking radiation, black holes slowly lose mass and energy over time, eventually evaporating entirely. If quantum hair exists, it might leave behind a faint imprint of the black hole's history, offering clues about the ultimate fate of the information it once contained. This could revolutionize our understanding of black holes and their role in the cosmos, shedding light on one of the most enduring mysteries in physics. As we continue to explore the quantum realm and the enigmatic nature of black holes, the black hole quantum hair theory reminds us that the universe is full of surprises. While the idea of quantum hair remains speculative, it represents a bold step forward in our quest to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. With each new discovery, we inch closer to unraveling the secrets of black holes and the quantum threads that might one day reveal the true nature of reality. Now turning to our 48th theory, we revisit the enigmatic phenomenon known as the cosmic dark flow. This mysterious movement of galaxy clusters through the universe has puzzled scientists for years, challenging our understanding of the cosmos and hinting at forces beyond the observable universe. The dark flow refers to the observation that large clusters of galaxies are moving in a specific direction at incredible speeds, as if being pulled by something vast and unseen. This motion cannot be explained by the distribution of matter within our observable universe, leading researchers to speculate that it might be influenced by something outside of it. The concept of dark flow first emerged from detailed studies of the cosmic microwave background, the faint afterglow of the Big Bang. By analyzing tiny temperature fluctuations in this ancient light, scientists detected a peculiar pattern. Galaxy clusters seemed to be drifting in unison toward a particular region of space. This motion defies the predictions of the standard model of cosmology, which assumes that the universe is homogeneous and isotropic on large scales. The dark flow suggests that there might be structures or forces beyond the boundaries of our observable universe, exerting a gravitational pull on the matter within it. One of the most intriguing explanations for the dark flow is its potential connection to other universes. In the context of the multiverse theory, our universe might be just one of countless others, each with its own unique properties and physical laws. If these other universes exist, they could be exerting gravitational influences on our own, creating the dark flow phenomenon. This idea opens up the possibility that the multiverse is not just a theoretical construct but a tangible reality with observable effects on our universe. The dark flow could be the first indirect evidence of other universes, offering a tantalizing glimpse into the larger cosmic landscape. The implications of the dark flow for the multiverse are profound. If confirmed, it would mean that our universe is not an isolated entity but part of a much larger, interconnected system. This would fundamentally alter our understanding of cosmology, suggesting that the laws of physics as we know them might vary across different universes. The dark flow could also provide clues about the nature of dark energy and dark matter, two of the most mysterious components of the universe. By studying this phenomenon, scientists might uncover new insights into the forces that shape the cosmos and the ultimate structure of reality. As we continue to explore the mysteries of the dark flow, we are reminded of how much we still have to learn about the universe. This phenomenon challenges our assumptions and pushes the boundaries of our knowledge, inviting us to consider the possibility of a multiverse and the existence of realities beyond our own. While the dark flow remains a subject of intense debate and investigation, it represents a bold step forward in our quest to understand the cosmos and our place within it. With each new discovery, we move closer to unraveling the secrets of the universe and the forces that govern its vast expanse. Now turning to our 49th theory, we delve into the fascinating idea that consciousness itself might be entangled at a quantum level. This theory, known as the quantum consciousness entanglement theory, suggests that the very fabric of our thoughts and awareness could be deeply connected to the strange and mysterious world of quantum mechanics. At its core, this idea challenges our traditional understanding of the mind, proposing that consciousness is not just a product of the brain, but may also be influenced by quantum processes. To understand this theory, we first need to explore the concept of quantum entanglement, a phenomenon where particles become linked in such a way that the state of one instantly affects the state of another, no matter how far apart they are. This connection defies classical physics and has been described by Albert Einstein as spooky action at a distance. Now, imagine if something similar happens within the human brain. The quantum consciousness entanglement theory proposes that the neurons and particles in our brains might be entangled, creating a network of interconnected quantum states that give rise to consciousness. One of the key proponents of this idea is physicist Roger Penrose and anesthesiologist Stuart Hameroff, who together developed the Orchestrated Objective Reduction, or ORCH, theory. They suggest that microtubules, tiny structures within brain cells, could serve as the site for quantum processes. These microtubules might facilitate quantum entanglement, allowing for the emergence of consciousness. If true, this would mean that our thoughts, feelings, and sense of self are not just the result of chemical reactions, but also involve the strange and unpredictable behavior of quantum particles. The implications of this theory are profound. If consciousness is entangled at a quantum level, it could explain some of the most puzzling aspects of the human mind, such as intuition, creativity, and even the nature of free will. It might also provide a bridge between the physical and the metaphysical, suggesting that the mind is not entirely bound by the laws of classical physics. This idea opens up new possibilities for understanding the relationship between the brain and the universe, hinting that consciousness could be a fundamental aspect of reality itself. However, the quantum consciousness entanglement theory is not without its critics. Many scientists argue that the brain is too warm and noisy for delicate quantum processes to occur, making it unlikely that quantum entanglement plays a significant role in consciousness. Despite these challenges, the theory continues to inspire research and debate, pushing the boundaries of our understanding of both the mind and the quantum world. As we explore this theory, we are reminded of how much we still have to learn about the nature of consciousness and its connection to the universe. The quantum consciousness entanglement theory invites us to consider the possibility that our thoughts and awareness are not just confined to the brain, but are part of a larger, interconnected quantum reality. Whether or not this theory is ultimately proven, it challenges us to think differently about the mind, reality, and the mysteries that lie at the intersection of science and philosophy. With each new discovery, we move closer to unraveling the secrets of consciousness and its place in the cosmos. Now turning to our 50th and final theory, we explore the Big Crunch theory, a dramatic idea about the ultimate fate of the universe. This theory suggests that the universe, which began with the Big Bang, might one day reverse its expansion and collapse back into a single point known as a singularity. Imagine the cosmos, currently stretching out in all directions, suddenly pulling back together, as if time itself were running in reverse. This concept challenges our understanding of the universe's destiny and raises profound questions about the nature of existence. The Big Crunch theory is rooted in the idea of gravity's relentless pull. If the universe contains enough matter and energy, gravity could eventually overcome the force of dark energy, which is currently driving the accelerated expansion of the cosmos. Over billions of years, galaxies would slow their outward motion, stop, and then begin to fall back toward each other. As this collapse accelerates, stars, planets, and even atoms would be crushed together, leading to a fiery, chaotic end. The universe would shrink back to an infinitely dense and hot point, much like its state at the moment of the Big Bang. This cyclical view of the universe suggests that the Big Crunch could be followed by another Big Bang, creating a new universe in an endless cycle of expansion and contraction. This idea, sometimes called the oscillating universe model, offers a poetic symmetry to the cosmos. It implies that the universe might not have a definitive beginning or end, but instead exists in an eternal loop of creation and destruction. For some, this provides a sense of continuity and renewal, while for others, it raises questions about the meaning of time and existence. However, the Big Crunch theory faces significant challenges. Current observations suggest that the expansion of the universe is accelerating due to dark energy, making a future collapse less likely. If dark energy continues to dominate, the universe might instead end in a big freeze, where galaxies drift apart forever and stars burn out, leaving a cold, dark void. Despite this, the Big Crunch remains a compelling idea, offering a dramatic alternative to the more widely accepted theories of the universe's fate. The implications of the Big Crunch theory are profound. If the universe were to collapse, it would mean that everything we know, every star, every planet, every atom, would eventually be compressed into a single point. This raises questions about the nature of time, space, and reality itself. Could information from our universe survive the collapse, or would it be erased entirely? Could a new universe emerge with entirely different physical laws, or would history repeat itself in an endless cycle? As we reflect on the Big Crunch theory, we are reminded of the vastness and mystery of the cosmos. Whether the universe ends in a fiery collapse, a cold fade, or some other unimaginable fate, these theories challenge us to think deeply about our place in the grand scheme of things. The Big Crunch invites us to consider the possibility that the universe is not just a one-time event but part of a larger, cyclical process. It encourages us to keep exploring, questioning, and marveling at the wonders of existence. And with that, we conclude our journey through 50 bizarre space theories that challenge reality. From the simulation hypothesis to the Big Crunch, these ideas push the boundaries of our understanding and inspire us to look at the universe in new and exciting ways. If you enjoyed this exploration, don't forget to like, subscribe, and hit the notification bell for more mind-bending content. The cosmos is full of mysteries, and together we can continue to uncover its secrets. Until next time, keep looking up. Now turning to the conclusion of our journey through 50 bizarre space theories, we reflect on how these ideas have stretched the limits of our imagination and understanding. From the simulation hypothesis, which suggests our reality might be a digital construct, to the Big Crunch theory, which envisions the universe collapsing back into a singularity, each theory challenges us to rethink what we know about existence, time, and space. These concepts remind us that the cosmos is far stranger and more mysterious than we often assume. Theories like the holographic universe and quantum entanglement have pushed us to question the very fabric of reality, while ideas such as the multiverse and dark matter galaxies hint at unseen dimensions and forces shaping our universe. The Fermi Paradox forces us to confront the eerie silence of the cosmos, and the Boltzmann Brain Paradox makes us wonder about the nature of consciousness itself. Each theory, no matter how bizarre, invites us to explore the unknown and embrace the wonder of discovery. As we wrap up this exploration, let's take a moment to consider the bigger picture. What if some of these theories are true? What would it mean for our understanding of life, the universe, and our place within it? The beauty of these ideas lies not in their answers but in the questions they inspire. They remind us that the universe is a place of endless possibilities, where even the most outlandish ideas can spark new ways of thinking. So, what do you think? Do you believe our universe is a simulation, or could it be part of an infinite multiverse? Is the cosmos destined to collapse in a big crunch, or will it drift apart into eternal darkness? Share your thoughts in the comments below, and let's keep the conversation going. If you enjoyed this journey through the mysteries of space, don't forget to like, subscribe, and hit the notification bell for more mind-expanding content. The universe is full of secrets waiting to be uncovered, and together we can continue to explore its wonders. Until next time, keep looking up and keep questioning the extraordinary world around us.